Today, I'd like to talk about essentially our work directed towards the development of new processes for chemical synthesis, mainly focusing on development of green chemistry processes. So as far as green chemistry goes, there's basically 12 principles that are involved, and essentially these can mean different things to different people. But for our purposes, what we're focusing on is essentially catalysis. And of the catalytic systems we're looking at, we're focusing on essentially the noble metals. These are really the workhorses of organic reactions. And of course, they fall into this category of endangered elements. So our thought process here is to develop catalytic systems based on these metals, and at the same time, hopefully develop more active systems that can operate in safer solvents. Namely, for organic chemists, we're talking about doing reactions in water, and that can increase energy efficiency, that is doing reactions at room temperature. Now, our initial target was the Suzuki reaction. Now, this reaction takes essentially two aryl groups and combines them into this diaryl system. And this is a privileged structure that's present in a lot of different drugs, most notably in terms of recent largely prescribed drug is losartan. It has this biaryl system, and this drug is prepared from this biaryl precursor. Now, these compounds are typically prepared through what we refer to as a homogeneous catalytic process. That is, essentially the metal is soluble in the reaction media. And this is great because it has high reactivity and high selectivity for these reactions. The downside from a green chemistry point of view is that these reactions are done in organic solvents. Oftentimes there's organic additives. That all contributes to the waste of this process. Also, there's limited catalyst recovery. Okay, you can recover the metal, but you're not going to recover the catalyst. And of course, since the metal is soluble in your reaction media, you can have metals, trace metals showing up in your product. So that's going to take you to another step of purification and essentially more waste generated. Okay. So our goal was to develop a heterogeneous process that could function as a reactive catalyst. Now, essentially, heterogeneous catalysis is great from a green chemistry point of view because you can isolate the catalyst very easily. It just filters out of the reaction mixture. It's not soluble. But limitations include low reactivity, thermal instability, metal leaching, and agglomeration. This is the metal clumps together and basically becomes unreactive. And of course, then to get these reactions to go, you have to use higher temperature. Where our goal was to essentially develop a heterogeneous catalyst based on a solid supported system that would essentially maximize the use of nanoparticles. Nanoparticles are small particles. They have a high surface area, basically have a much more reactive environment than essentially amorphous materials. And so our approach then was to find a solid support that would exploit our nanoparticle chemistry. And to that end, we began looking at the clay halloysite. Now, halloysite is a natural clay. It's mined out in Utah, and it comes out of the ground looking like this chalk, but it has this fibrous material, which are actually nanotubes. And these nanotubes basically are empty inside, maybe with waters of hydration, but basically you can fill these with different types of molecules. And we thought this would be a great place to put metal nanoparticles to stabilize them and essentially provide a reaction surface for them to work at. Now, our intellectual property basically surrounds essentially the preparation of these nanoparticles and encapsulation in the halloysite. We were the first people to put palladium in here, but others had put in gold and silver. But really, our intellectual property focuses on the fact that we do this all in water. Okay, we make these nanoparticles in water. They enter into the tube in water, and basically we get this nanocomposite, which here we have a TEM image. You can see the little nanoparticles inside the tube. And this process gives us about 98% encapsulation of the metal. Overall, it's about 4% weight by palladium based on the material. But essentially, this gives us an air-stable material that it turns out is highly catalytic. Now, when we applied this to essentially some Suzuki coupling reactions, we found that we could catalyze the reaction quite nicely with low metal content, basically about 4%, 0.4% metal. The reaction was very tolerant of a variety of functional groups, but more importantly, we could execute this reaction in water, or water ethanol, or water propanol, basically these aqueous solvent systems. But what really caught us off guard, we didn't anticipate, was how much the reactivity of this system was enhanced. Reactions take place at 25 degrees, and typically reactions are complete in 1 hour. Okay, so that's a tremendous enhancement over essentially traditional coupling catalysts. Now, we extended this chemistry to that losartan building block, and we found that we could make this building block in 98% yield on a 2-gram scale. But more importantly, we found that we could take the catalyst, filter it off, and then add it to another system and repeat. And in the next batch, we didn't lose any activity. We could take the same material and keep recycling it again and again. And essentially, it wasn't until the 7th or 8th time that we saw yields start to diminish. So this greatly extends the lifetime of the catalyst and the utility of the process. Now, we've since developed this chemistry for a copper system. In the copper system, we are applied to the multi-component cycloaddition reactions for the synthesis of triazoles, or green click chemistry. The advantage of this system, again, is we can do this reaction completely in water, but we also don't have to isolate this treacherous alkyl azide. Basically, we can go from a starting material to product cleanly and in high yield. Again, these triazole, we made a triazole that is sorry guys. Okay, we made a triazole that essentially is a precursor to rafinamide. This is a anticonvulsant being marketed as Banzel, but essentially, again, all in water. And again, we see the same level of recycling in terms of being able to use that catalyst again and again. Here, 4 times past the initial use without really any reduction in yield. Now, we have additional catalysts that we have developed, and essentially this is our latest one. This is an ionic liquid palladium system that essentially allows for essentially Heck coupling. This reaction produces these cinnamic ester types of intermediates, which are prevalent in things like sunscreens. Okay, and so this chemistry again can be done completely in water and has this. We haven't quite finished the recycling experiments, but at least so far we've gone through 2 or 3 cycles with this material. And so overall, this has a high level of reactivity, much higher than the catalysts currently used for these type of reactions. So the advantages of our systems, basically, they're easy to execute. A lot of these catalysts we're using currently in my organic labs with my students. Okay, we use this in one of the teaching labs for them to do it. Okay, they can handle it easily. We get excellent recyclability, and essentially the amount of trace metal is very low. Okay, in the sense the halocite tends to hold on to the metal, and essentially reaction times are very short, accelerating through output throughput. Now, we haven't done this on large scale yet, but we can set up 10 reactions right next to each other and make 20 grams of material in an hour. And essentially, last but not least, these nanocomposites have a long shelf life. They're air stable. You don't have to work in a glove box to load catalysts, and so they're very, very convenient in that way. Okay, well, with that, I'll be happy to answer any questions, and thank you for your attention.
Sorry, looks like oh, one question.
Yeah.
Well, first, I'm thankful for making this as easy as even a caveman can do it. Um, when you make your nanoparticles, in this case, the nanotubes, uh, do you have a process to make them consistently, reproducibly, so
Yeah.
you can, get repeatedly,
Yeah,
the same results?
the process is different for every metal, but the nanotubes are natural. Okay, so we don't have to do anything with those. We just take the commercial material, just wash it with water, and then can prepare the catalyst either one of two ways. We can form the nanoparticles first, and then let them diffuse into the particles, or we can simultaneously form the nanoparticles with the tubes present. And so consistently, we get reproducible encapsulation for each different metal. And different metals require different reducing agents to get them in, but basically in each process, we've been successful in reproducing that again and again.
Thank you.
Mhm.